Welcome everyone to the Shannon Memorial Lecture. In case you're wondering why I'm introducing Rudy and not Paul, I'm wondering that myself too. So when Paul asked me to introduce Rudy, I was actually a little bit unhappy because I always look forward to Paul's introductions. I always learn something new from them, like Shlomopedia or Yada Ababa Abbas, or things like that. But Paul explained that I've known Rudy for a long time, and it'll be very easy for me to dig a lot of dirt and share it with you. And of course, as always, Paul was right. In fact, so right that it would just have been a little too easy and maybe a little bit unfair. So I thought that for a change, I'll give a technical introduction. So, okay, and just maybe let you tell you about some of Rudy's achievements and the high esteem that his colleagues hold him at. So, for example, just this year, Rudy was invited to give a plenary talk at the Information Theory Workshop, a plenary talk at the Zurich workshop, a plenary talk at CIS in Princeton, a short course at the European Information Theory School, a short course at the Asian Information Theory School, and of course these two talks, and I probably missed something, Google missed something, Rudy might tell us. So you probably think that therefore his life is very easy and he's just going to come here and just spit out his standard talk. But in fact, Rudy insists on giving a different talk every time he speaks. Every time he presents a completely different talk with different material, different results, different slides, even different jokes. And you'll see that tomorrow. And in fact, I think that the only thing that stays the same throughout all his talks is his blue shirt that you can see. So, so going back to his achievements, so as I think you all know, along with, of course, Paul and Alex here, Rudy is one of the world's leading authorities on error correction. And as such, he has devoted his life to removing randomness. So eliminating random errors from messages, wiping out spectral noise, proving concentration of random algorithms, and showing that they converge to the perfect answer. In fact, he has recently even moved from the random LDPC codes to the deterministic polar codes. And actually, some of these trends have rubbed off on his personal life. So over the years, he has removed randomness, eliminated prior errors, concentrated his efforts, and converged on a single, perfect, deterministic, spectrally noiseless answer. And that's the blue shirt that he's wearing. So, okay, and speaking of his personal life, as you must have guessed, he is as conscientious about that as he is about his professional life. So after he moved to Switzerland, he actually sold his car and he started biking to work every day. It's about 15 kilometers. And he also bought a transport bike. I'm not sure if you have seen it, but a bike that have some, some stuff in the front, which he uses to carry groceries and sometimes his girlfriend. And he bought an apartment in a zero emissions building. And most importantly, he embarked on a single shirt policy. So just to finish, I say that anyone who even slightly knows Rudy knows that he always strives for the best. His bounds are the strongest, his proofs are the clearest, his algorithms are the fastest, as we'll see. His codes have the lowest errors. His bikes are made of titanium. His writing implements, like this brass and gold Midori pencil, are the finest and the sharpest. And his blue shirt is the best that Marshalls carries. So with that, let's welcome Professor Rudy Blue Shirt Urbanke. Thanks.
Thank you very much, Alon, for this very nice and kind introduction. And thank you very much for the organizers, Paul, and also Alon, and whoever helped for this amazing honor for me to be here and to talk to you. It's great to be here. Over the past 10 years, I probably have been here in San Diego 15 times. But I arrived here yesterday evening, and I thought that this time somehow is a little bit, it's somehow different. And of course, one thing is different because it's an amazing honor to give this talk here. But then I was thinking there must be something else, and I figured that I figured it out why. I've been here now probably about 12 hours, and even though I've been here about 12 hours, probably slightly more, Alon has not asked me yet to schlep some big things back and forth or to do some last-minute preparation, so to come up with some jokes. So it feels very relaxing and very pleasant to be here. Okay, so thank you very much for this opportunity. Now, I should also thank Hamed Hassani, who graduated from EPFL and is now at ETH, and he helped me, I'll mention some joint research, but also he helped me, of course, with putting up these slides. Now, what do I want to talk to you today? I'll talk to you today about the basic general setup that, of course, was put up by Shannon in '48. And we're just talking about the simplest setting, point-to-point coding, where we have, typically a discrete memless channel. So we have a certain channel transition probability. We have an input alphabet, output alphabet. The channel has a certain capacity C. And we have a certain decoding algorithm in which we estimate what the transmitted word was given the observation. And we are interested in error probability and, of course, want to keep this small. And we typically talk about the case in which all these quantities are known, at least the channel itself. Now, what I want to do is, the last so many years, maybe 10 years or something, there have been quite a few new coding techniques, in particular polar codes, and I'll talk about also spatially coupled codes, that have come up and that look promising. Now, just as maybe to set the stage, neither of these two techniques, polar codes or spatially coupled, are currently already in products, but they are at least promising, I think, and I think they have the potential that perhaps in a few years they might be in products. For example, spatially coupled, I know that Frank Chishang has some concrete proposal, for example, for optical transmission. It's called staircase codes. I don't know if these things will get into a standard or not, but at least they I think, close enough, and they're very interesting, and at least in our community, the academic community, they have created quite some interest. And so what I want to do is I want to first tell you a little bit what these two things are about, just to set the stage, because I guess not everyone here is necessarily an expert. And then I want to tell you a little bit about how these two compare, even though the way it was set up is as a competition. That's not really the point. I want to just somehow see what are the advantages, disadvantages, how do things scale, and then maybe phrase what I perceive to be probably the biggest open question that we have in this area. So let me get started a little bit to set up the first one, polar codes. And of course, I know that some of you are experts in here, and I apologize for repeating the obvious. Polar codes were invented by Erdal Arikan just really a few years ago, and so here's how they work. Now, we have, as seen beforehand, the general channel here with input and output, input X and output Y. And so the basic transform in polar codes is to take two of these instances, two independent instances of this, and for the input here to simply connect them by an XOR. So think of everything as bits, and I simply have here a linear transform of the two bits U1 and U0 into the bits X0 and X1. And I'll always think about, on the left-hand side, this to be the information, and I'll think about this as the code word, and we'll talk a little bit more what this means. And then these two things are transmitted, and the outputs are Y0 and Y1. So that's the basic polar transform. Now, the basic idea is to take this transform and to repeat it recursively. So take two of these instances now, and now to play exactly the same game with like channels. So I'm going to play the same role, the same game now with these two like channels that I have up here and these two inputs that I have up here, and put another one of these transform in here. And this way I create now from a set of 4 inputs, a set of 4 outputs via this transform. It's just a linear transform here over the bits, over the XORs, and I transmit it. And so I'll do this a repeated number of times. And at that point, it might not be very clear why I want to do this. So this is now going from 8 to 8 and having the output. And in general, when you think of coding, of course, you should think of perhaps 1,000 bits or perhaps 10,000 bits. But of course, all my examples will be small, maybe 8 by 8 or something like that. OK, so that's the basic transform. Again, I will think of this as my information, and I'll think of this as a code word. But of course, currently, this is simply a one-to-one map. This map might not be, it's made up of invertible maps. And so this whole map is still invertible. And so, of course, I have the same number of possibilities in here. All the possible code words, if I put in here, I get all possible information words. I get all possible code words. So this itself is not a code because it's just a one-to-one mapping. So we'll have to still play a little bit. And the missing ingredient is really the decoding algorithm. So I'll first explain how the decoding works, and that will then make it clear what actually the code itself is. And the decoding algorithm is a successive one. And the way this will work is that you see here an order, U0, U1, U2, U3. So we'll decode in this order in a successive manner, always assuming if I'm decoding channel UI or bit UI, that all the bits beforehand are known at that point, and that all the bits afterwards with index larger are completely undetermined, and they're just 0, 1 with probability half, okay? So let's start with U0. Let's assume I wanted to decode U0. I know nothing about these bits here. They are assumed to be random, but I know my observation here, okay? So what would this correspond to? Well, if you draw the paths, so you put here bit U0 in here, you know that here, and you're thinking about what can I infer about the U0. If you think a little bit, it takes a little bit some thinking, you will see that this is equivalent to the following channel. It's a channel in which you have, on the bottom here, your 8 bits, okay, in this case, and in which all these bits are XOR, so they're just XOR together. So you can think of that just all these bits here XOR together. And what you have, the U0 is the XOR of all the original X's here. But what you observe are not the X's. What you observed are a perturbed version of the X's. Okay, so from this vector of 8 X's, whose XOR is the U0, and you have perturbed version of that, you want to figure out what the U0 is. Now, that's the channel that's seen for U0, or that's the decoding task that you have to fulfill. That's a fairly terrible channel, right? Because if you XOR things, things get worse, the noise will add, and so on. So that's a fairly bad channel. So you will not get, it will not be a very reliable transmission from the output here. But that's what it is. So let's assume by some miracle we know now what the U0 is, and I'll just draw it. It's equivalent to draw it like a complete binary trees in which I have simply XORs at each of this position here. Let's assume we knew what U0 was. And let's assume now I want to see what the decoding task for U1 would be, given the vector y, and given that I know already what the U0 is. And if you draw it, and again look a little bit, you will see that this is exactly the same, except now in this tree, you don't have everywhere XORs, but now you have in the root node here a repetition. Okay? So this is slightly better. So you get an XOR of these bits, and the XOR of these bits supposedly is exactly the same as the XOR of these bits, so you have a repetition, twice the same thing, but down here you still have XORs. Okay? And so again, you have noisy versions here that you observed, and you need to figure out what this bit here is. All right, so this is a slightly better channel that you see. And if you look at all of this, you will see that they all look like this. They all are these trees, and the height is simply how many recursions we did, right? But what is different is that depending on which one you're looking, so you're seeing these 8 bits when you decode them, what's different is that what depends on is what operation you see on the level. So what happens is for each of these 3, you will see in each of this level the same operation, and there are 2 possible ones, either an XOR, which is here an empty ring, or you will see an AND. Okay, so for example, this channel is one in which you see 8 times the same bit, okay, and each of them will be noisy version. This is where you have the XOR of 8. So this is the best channel you see. You see a repetition code of length 8 here. This is the worst channel, and in between you have some other kind of channels, and the ordering there in between is not so completely clear, okay? That's quite a little bit more complicated, what's good and what's bad. Okay, so these are the tasks under successive decoding, fine. And again, you should think of very large trees. And so what is now the punchline that you get? The punchline is the following. If you do this for a very large code, so not just the length 8, but you do this length 1,000, length 10,000, then you have exactly the same interpretation. But what will happen is here the following. Out of all these indices, these channels that you have here on the left, there will be some that are good and some that will be bad. Good will mean, it means that if you do this decoding task in the successive one, that this channel will be very reliable. Okay, with high probability, just doing the decoding now along the tree, solving this inference problem that I've shown you, you will be able to determine what this bit is. And there will be some other ones which will be bad. For example, think of the very first one, the XOR, which if you do this decoding task, you basically can have no inference. There's basically no information, no bias that you can have, simply given the observation that you have on the bottom, okay? And the miracle of polar codes is that if you look at this for large ones, the number of bits or the number of channels that are good will be very close to the fraction C, which is the capacity of the original channel. And then by inference, by exclusion, the number of bad channels, so the point is that they will polarize to either being very good or very bad. So this is basically a partition of the space, and the bad ones will be then 1 minus C, right? And so how do you do now the decoding in this case? Well, very easy, the idea. What you do is you simply pick the good such indices that you can decode, and you pick the good ones, the blue ones here, and you will put information here. So that's the bit where you put information, okay, here, here, and here. And you pick the bad fraction, so the red ones here, which you can make no inference, in which you cannot do the decoding task, and you will simply put some known fixed information there. And this information will be known at the receiver and the transmitter. And so if you look, for example, in this case, 4 of the bits are blue, so this is that carry information, and 4 of them are red. These are bits that are fixed and so don't carry information. And so this means that now the map will not go from 8 to 8, but it really goes from these 4 bits to the 8 bits, right? So you really now you have a code of rate a half, and you expand this vector now here where you have only 4 degrees of freedom, where you fill in information, you expand it to a vector that has 8, you transmit it, and the decoding is exactly done as beforehand, as I explained, by doing successive decoding. And this scheme works, namely you can prove that if you have large enough codes, you do exactly this low complexity decoding algorithm, that you can get arbitrarily close to capacity. And complexity, as I'll talk a little bit later, is fairly low, and I'll tell you exactly what this means. Now, one picture that will be nice to have is like this picture like this. Think of this as all these bit positions that I have here, and I call them sometimes channels, okay, of all the 8 channels that you have here, and think of the blue ones as the good ones, okay? So there will be a fraction of good channels. These are the ones that you use for coding, and that fraction will be very close to capacity, okay? And we'll see this picture a little bit later in some slightly more complicated scenario. Good, so that's all I will say about polar codes. Now, let me now get to the second class of codes, for, and I want to compare polar codes with this. Now, what are spatially coupled codes? Spatially coupled codes are low-density parity check codes or graphical codes. So these are codes in which, a special class of codes in which there's the following encoding or the following pictures. Think of them as these are the set of bits, and again, I just show a few of them, okay? But again, you should think of this perhaps as 1,000. Think of each of them as a parity check, so a linear constraint, which puts certain constraints of this bit. So this check says that this bit plus this bit plus this bit, the XOR has to be 0. And so this code itself is a standard low-density parity check code, a standard graphical code, as you would find it now in many of the products in the form of either turbo codes or LDPC codes. They're just different, slightly version of the same picture. And I tell you a little bit more of how actually, how you will use these kind of codes. So this would be a standard code which has been studied and introduced originally by Gallagher, and since the rediscovery by Beroux and Clavier in '93 has become quite a hot topic, and there are thousands of papers of how such codes should be designed with the respective iterative decoding algorithm. Now, what I tell you is now a particular version of these kind of codes, and the version is if you now introduce some spatial structure, and this goes as follows. So don't just take one of such copies, but take many of these copies, okay? So think of them maybe as 10 or 20 such copies. And just so that I can depict them in a slightly nicer way, I will depict them in a circle, okay? So you think of these as 20 copies, each copy being already a reasonably sized code, maybe of length 1,000, and you put them around the circle. Now, as it is right now, this is a completely standard LDPC code, or 20 of these completely standard LDPC codes. That wouldn't be very interesting. Now, what you do now is that you will take these codes and you will connect them, okay? So you will spatially couple them. And there are many ways of doing this, but if you have seen, in this picture here, the idea was that you take one of these edges that you have here, and you will simply decide, let's say randomly by flipping a coin with, let's say, 3 sides, whether or not you leave the edge within the code the position that you have, or perhaps you connect it to your left neighbor, or perhaps you'll connect it to your right neighbor. Just think of a picket fence or something like that, okay? And you can do this either randomly or can do this in a more systematic fashion. I'll show you a few pictures what this could look like. And you're not just going to do this for one of these, but you're going to do this for each of these edges, okay? And so you will come up with, let's say, perhaps a picture like this. Now, the important thing, and this might not be apparent from this picture, is that you do this in such a way that the degree structure stays preserved. What do I mean with this? Typically, such codes are designed by specifying how many nodes there are of certain degrees. So for example, you might say that maybe 20% of these nodes are of degree 3, and maybe 40% of degree 4, etc. Okay, and the same thing for the check nodes that you have here. And so when you do this structure, when you do this spatially coupling here, you do this in a way that still locally the degrees are the same. So there will still be 20% of degree 3 and maybe 30% or whatever I said before and of degree 4. But now the connections are not just all within the position that you have, but some of these connections are within, but some of the connections go to your left neighbor, some of the connections go to your right neighbor. Okay? But the local structure is the same. Now, if you take something like this, what you get is something completely circular symmetric, and that wouldn't do anything interesting. It would behave exactly like the standard code that you have the underlying code, so it wouldn't do anything. So what you need in order to see something interesting is you need to break the symmetry that you have in here. And there are many ways, again, to break the symmetry. One is the following. You simply take one of these. So let's assume connections only go to your left or right neighbors. You simply take a window and simply imagine now that you cut this window. Okay? Now, how could you cut the window? One way to do it is the following. Let's assume that I would know that these positions are fixed to some fixed values. Okay? So similar to what we did in the polar code case. Let's assume that I say that all these positions, these bits are known, and let's say fixed to 0. And this is known both at the receiver and at the transmitter. Well, if that's known, and then what this means is that the contribution it would give to any of these check nodes here, while it's a known value, it's a particular value of 0, it's the same as if these positions weren't actually there. Okay? So now we have virtually cut it. And so now you have a cut such chain. Okay? And now, of course, it's slightly more convenient not to look anymore at it in a circular fashion, but simply to think of it as a linear fashion. Okay? So now this is exactly the spatially coupled structure. Okay, so I have not told you right now why we're doing it, and I'll get to it. But let me first show you what are the important parameters and maybe a few more pictures because we'll need them later. So what are the important parameters in such a representation? The first one is this W. I will not dwell much on it, but this has to do with how locally you connect things. Okay? In this case, W was just 3. You could just either stay where you are, you could connect it to your right neighbor or to your left neighbor. Okay? So there has to be some degree of connectivity. You might decide that you connect maybe to the right or to left or to right or something like this, but there's a window in which you do the connection. The second parameter is the length. Okay? So think of each of them as originally as a code. I will call these positions. And so you will have maybe L of these codes that are coupled together. Okay? And you should think of that as perhaps as 20 or something like that. And then the final one is the dimension here. Remember, each of these positions is like a usual code that you have. So you should think of that as at least hundreds or perhaps 1,000 or something like that. Okay? So you should think of the M. And so these are the parameters that we have. And then there's still the local structure that you have. So for example, maybe every node here has degree 3, every node has degree 6, for example. Okay, so this would be then a 3, 6 with connectivity 3 and maybe a length 20. So these are the parameters we have. Okay, so now there's several ways of how you can do this. One way is you can simply think of doing the connections randomly. So you pick a certain window, and within this window, you pick randomly where you connect to. A scheme that is maybe slightly nicer to do in practice is to do this in a very regular fashion. So this is a representation which is a slightly different ensemble but has the same properties, in which if you look at a node here, every node here, this is a node of degree 3, and every node has one connection on the same level, one connection, let's say, 1 to the left, and one connection 2 to the left. Okay, so this is now in this representation, it's completely regular. And now the question is, you can see there's some edges that go outside. So what do you do with these edges that go outside? Well, so this should go still to variable nodes. So these are checks. These are still variable nodes it should go to. Well, how could you deal with it? Well, one way you deal with it that you simply say that these values are known. So these values are, let's say, 0 and 0, and are known both at the transmitter and the receiver. And here, this should go to check nodes. So you simply have to add these check nodes here. Okay, so the global effect will be something like this, and sometimes I'll just draw it like this. You can just take this middle part and shift it a little bit to the left. But you will see always pictures like this. So this is a code in which this length, I don't know, is perhaps 20. So there are 20 such codes in here. Each of this is a representation of a code that has perhaps 1,000 nodes in here. Every variable node has degree 3. Every check node has degree 6, except at the boundary. Okay, so that's now a spatially coupled code. Now, why would one do such a thing? Okay. Now, the important thing is that there's something very nice and interesting happen that when you couple things together, and you simply use the standard iterative decoding algorithm that you would do on graphical models, okay? And so what happens is, and I'll just show you now a movie that's running, what happens is the following. If you ignore the boundary for a second, inside, the code doesn't know that it has a special structure. The code inside behaves exactly like you would have taken a 3/6 code in this case and simply did iterative decoding, and it will have a certain performance. But if you look at the boundary, what happens is that you see you have more check nodes. Check nodes are like extra information, are further constraints. So on the boundary, the problem is more constrained than in the middle. And if you pick it in the right manner, then what happens is that even if you decode at a noise level that's typically the 3/6 code could not decode, since the decoding problem is easy at the boundary, an interesting effect will happen at the boundary. At the boundary, you will start decoding, and you will start a certain decoding wave. Okay, so let me just show you what happens. So what do I show you here? So this is the spatial dimension here. And I apologize, you don't see very clearly. So these are lines. So this is maybe something of 100. Then I pick maybe something of 100 codes in here or something like that. So, and what I do, I show you here, I show you the local error probability. So what I show you is I do the iterative decoder, so you will see some iteration happening. And this will be the error probability that you see. Originally, this error probability is 1. And as we start decoding, you will see that something starts at the boundary, and this effect will move in like a wave. So let me just show you this. Oh, boop, boop, boop. Sorry. So let's just run this. So you see that things happen at the boundary. So even though in the middle, it behaves exactly like the standard code and couldn't decode, there's something interesting happening at the boundary because it's easier at the boundary. And this effect, just like a solitone wave, will go, and it will simply go unhindered like a solitone. There's no decay that happens. Okay, it just goes on at constant speed. And it will be able to decode even though the underlying code itself could not decode. Okay, so that's the interesting part that happens. And so, what is now the summary for these kind of codes? Well, if you take this kind of code, what happens is the following. If you simply use, for this kind of spatial coupled code, a standard iterative decoding algorithm, BP as it's standard now in many of the products we have, either in the turbo code setting or the LDPC setting, then this code will decode as well as if you had taken the underlying code, let's say the 3/6 one, and had been able to decode it under like map decoding, the optimum and typically exponentially complex decoding algorithm. Okay, so under low complexity BP decoding, this code behaves as good as if you had taken the underlying code and had decoded it in an optimum fashion. Now, so that's good news. It's not all good news. We pay something, and what do we pay? We have some extra degrees of freedom that we lose at the boundary here, right? So we pay a price. The rate of this code is not exactly the same as the rate of the underlying code that I have in the middle because I'm using some extra degrees of information, some extra degrees of freedom here that I'm using for the check nodes. And so because of that, I will pay some rate penalty, and overall the code will be something smaller. And so that means that I cannot pick this dimension too small because you can see that this rate loss will be proportional to 1 over the length of this code because it will be amortized of this thing. So maybe a physics analogy is the following. We have a process, okay, that needs to get started. Okay, the starting point is to get this wave started. And so think of it as a large ball here that you need to get started. So in order to get it started, you need to push it. Okay, so you need to push it, and the push is exactly this extra degrees of freedom that you give. Now, once you push it and there's no friction, which happens in the system, it will roll no matter how long you want to roll it. So it doesn't matter how long you take the chain. It will still do the decoding. And it happens that even at the end, you will be able to kind of gain back some of the momentum. But unfortunately, at the end, there's still some loss that happens over the length. You will not be able to gain all the momentum that you put in. Okay, so there's some inherent rate loss that you have. Good. So now I have explained to you the two schemes. The question is, how can we compare? Okay, so of course, there are many ways you could compare. Let me just pick some fairly obvious one. Well, we have the capacity of the channel. We have the rate of the code we're interested in, of course. And so, clearly, we'll look at these two parameters, right? We'll hope that we can transmit close to this capacity here. Now, then very important will be, of course, the block length, right? So how long a block length do we need to transmit at a certain rate and a certain probability of error? And so we'll in particular be interested in how things scale in the block length, right? And so that will be an important parameter. And then, of course, we have the, let's say, block or bit error probability. And this, of course, will be a function of the length and the rate and the capacity. And we'll also have to talk a little bit about the complexity of the two schemes. OK, so now let me go through some of the parameters that we can look at. Now, if you look at how easy to prove, so both of these schemes are able to, I guess I didn't say this explicitly for the spatially coupled code, both of these schemes provably achieve capacity when the length becomes large for, certainly for all binary input memoryless symmetric channels, but for a much, much larger class, okay? So both of them are provable, but if you look at the actual proofs, polar codes are unbeatable if you look at elegance and simplicity. So this is something that you can do in an information theoretic class, perhaps in 2, 3, 4 hours, rigorously, even for general channels, for people that have absolutely no prior background in coding. Okay, so that's something that's fairly easy to do. Spatially coupled typically is quite a little bit more complicated to prove. So certainly when it comes to ease of exposition and elegance, there's no competition. Polar codes are a fantastic choice. Now, one of the most important things is to see how things behave in the length, in the block length. And so maybe just to get some idea, how should things behave? What's the best thing we can hope for? And there's some very nice work starting with Strassen in the 60s and then some beautiful papers by Yuri and Vince and Sergio about the optimum finite length behavior of codes. And let me just state this here for the BC because it's simple. So how should, for the optimum code, how should these parameters relate? And what this says is that there is a fairly simple relationship between the block error probability. Q is just the Gaussian error function. Then the rate is the rate. The epsilon is the channel parameter. So this is the difference, the gap to capacity. 1 minus r minus epsilon is how far you're away from capacity. N is the block length. So you're saying the product of these two things divided by epsilon 1 minus epsilon. Okay, now I write here a tilde in here, and I'll tell you a little bit more. This is not an exact identity, but it's something that as this product here stays constant, but n becomes large, this becomes exact. Okay, so now if we're looking at this thing here, so there are two main parameters, the block length n and the rate. And so this says that the optimum, so this is feasible here if you want the block error probability, which is on the left side. So meaning you have a channel that's better. Okay, this is the epsilon here. If the channel is better than that, this whole regime you can fulfill. You can pick any point here, and there's a code here. And this on the right, to first order, you should not be able to achieve, right? So capacity just tells you, the rate or the optimum rate you can achieve. This is much more detailed. It tells you how the parameters, probability of error, capacity, and rate relate even in the non-asymptotic limit. And so if you now change, right, so for example, we're changing the block length, then this simply changes the steepness of the curve, right? As the block length goes to infinity, this will simply be a straight line down, right? And as you have a block length that's not 1, this will not be exactly straight. So let me just show it again, right? So if I make the block length larger, then this will become steep, and in the limit, this will be exactly a line. And if it's less, then this will be this. And the other thing will simply, if you look at the rate, this simply will, where the threshold is, this will simply shift essentially in a linear fashion, right? So that's what we should be able to do. Now, how do we compare now when we actually look at coding? Okay, so now this is for the optimum code. So what should we be looking at for actual, if we have a coding scheme like the one I showed you? Well, typically what you will see in talks, you will see here the following. You will see here all these curves, right? And so you will typically see here a measure of channel quality, let's say erasure probability, SNR, whatever you choose. And then here you will see probability of error, typically in a log scale. And you will see here as a function of n, the various curves. And typically, for all these schemes that we talk about, there will be thresholds. So there will be the equivalent of capacity. So for example, for polar codes, the threshold is exactly capacity. For something like LDBC codes under BP decoding, there will be also a threshold in the asymptotic limit, but it might not be capacity. It might be some slightly different threshold. But what you will see is, for any such scheme in which you keep everything the same, the rate and all the decoding algorithms are the same, but you increase the length, you will see that these curves, these finite length block error probability curves, will increase, and in the limit, they should become simply step functions here, right? Now, the important thing is when you want to, so how should you now analyze kind of how this code behaves? Well, one popular thing is to look at error exponents. Error exponents are if you fix the gap to capacity, and then you're looking at the block length and make it larger and larger, and you're looking how the error probability decays. And for good codes, this decays exponentially, and you're looking at how this, what is the exponent, okay? How does it decay? What is the exponent? Now, my claim is that for engineering purposes, an even better way of doing it is to look at this finite length scaling where you do something slightly different. You're thinking of the error probability fixed, so you're fixing this thing here. And now what you're looking at is how do these curves here approach the asymptotic limit. Okay, so you're fixing the error probability, and now you're making n larger, and you're checking how much closer can you get the gap to the threshold. Okay, so that's another way of scaling, and I will call this the scaling law. And so the question is, in order to think about it, is the way to do it is instead of plotting here the channel quality, is to plot a slightly different version, a scaled version. And so the scaled version should depend on the parameters. So this is the threshold that you have. So that's the gap to capacity. That's the epsilon in the transmitting. That's, let's say, the gap. That's the optimum capacity. So that's how far you're away. That's this distance here. And now you should try to see if you can find a proper scaling such that all these curves will collapse. Now, the question is, why should it be n to some power times this? Well, it turns out that in physics, you have many such situations where you have thresholds and you're looking at the finite length scaling. And a very, very standard way is that you have a scaling in this form. There are situations where there's scalings of different forms. Maybe there's log n in front. But it's surprisingly how predominant scalings of this form are. And indeed, these are the right scalings for our case. So the only thing now you should try to see is if you're changing the mu, can you change the mu in such a way that these curves to first order will all collapse to the same curve. Okay, so can you find the right scaling? If these curves to first order collapse, what it means to first order, it means that as n becomes large, but this product stays constant, they will converge to the same curve. If such a thing can be proven, then we're saying that this function here is the mother curve, and we're saying that this exponent here is the scaling exponent. Okay? So how would this work now for the best codes, for the optimum codes? Well, if you look at this here, right? Now, the scaling function here would simply be the Q function, right? So, and now you can see that in here, the right scaling, or the scaling n appears with square root. So it turns out that this mu that we're looking for here in this case is 2, okay? And and this is simply the gap to capacity. Okay, so you have the gap delta here. I often write now delta, which is the gap to capacity. And so the right scaling here will be that you should think of delta, the gap to capacity, times the square root of n to be a constant. And that essentially determines what the error probability is. Okay, as long as these two things scale as a constant, that to first order determines the error probability. And that gives you the trade-off between how close you are versus what the length is. Okay, so that's the right scaling that you should have. So that's for the optimum code. And it's fairly easy to see that there's nothing, why this cannot be better than square root of n. Just think of, let's say, the erasure channel, right? You're having n possible channel outputs. You have n times epsilon expected erasures. But just the variation in the channel is of order square root of n, right? I mean, that just will be of this order. And if you divide square root of n by n, that's exactly, again, you come up with 1 over square root of n, and that's exactly this exponent that you have, okay? So it's clear that this is just a variation in the channel, and indeed, you can get as good as that. Okay, so in another way of saying is that we know that the block length should scale like 1 over the gap to capacity squared, okay? So that's how the best thing we can hope for. So how do our codes behave? Well, for spatially coupled, we don't have a rigorous proof. What we have is we have a channel, we have a model of how we think that a decoder really works, and then that model we can analyze rigorously, but that's not the same as analyzing rigorously the whole chain. And you can see here simulations. So this is, again, probability of erasure here for the erasure channel block error, and some of them are the actual simulations. The other ones are the predictions. And for this model, the scaling behaves in the following way. And I don't think I want to go exactly over all the details. For example, you see some obvious things. You see that, for example, the block error probability scales like linear in the length of this chain. Okay, that makes a lot of sense. Why? You have seen that the decoder is basically a wave that moves along at constant speed. And essentially, what can happen at any point in time, it could happen that this wave stops. Okay, there's in some position, there's some unusual number of errors in here, and the wave could simply stop. And that probability, if the probability itself is fairly low, is simply proportional to the length of the chain. Okay, so that makes a lot of sense. And then what you can see is that this is simply the CDF of the Gaussian, and here you see e to the c squared. There's no minus in front. So that's something that's exponentially growing. And you can see there's an integral, and this integral goes from 0 to something, and what goes is the square root of m. So remember, m is basically the local block length that you have, times delta, the gap. So you can see that here you have, again, the square root of m times delta. But m is not the whole block length. M is only the local block length. The whole block length is L times m. So this would go exactly as the optimum scaling there is. But unfortunately, there's still the parameter L. And unfortunately, there are two things that you have. You have a loss because things can simply get stuck, and you can have a decoding error. But you also have a loss because, remember, we can't pick this too small because there's an error loss that there's a rate loss simply we get from the chain length, because we had to use a few extra positions. So if your whole block length, you need to put some length in here, and you need to put some length in here. And if you figure out what's the optimum way you can do it, you will see that the scaling goes like 1 over delta to the third. Okay, so that's not as good as the optimum thing. 1 over delta to the squared is the optimum one, so you need longer block lengths. Okay, so there's still something that it could do better. Now, what happens for polar codes? Well, for polar codes, it's a little bit harder to explain where this comes from, but we have rigorous upper and lower bounds on the optimum scaling. So it turns out that the block length, and that depends, there's two reasons these two numbers are not the same. The one is that our bounds are not tight. The other one is that the scaling actually depends on the channel. Okay, so it depends if you have the BEC or the Gaussian. These are not the same. But you can see that it's somewhere between 1 over delta to the whatever 3.5 and 1 over delta to the roughly to the 6th. The true thing, you can do back of the envelope calculation, is about 1 over 4. Okay, so the true thing is about mu is 4. And so this means that if you simply do it like this and you don't do anything else, then it means you would need a block length in that limit, which is roughly the square of the optimum block length. Okay. Now I'll tell you a little bit more then later on that there's many things you can do. For example, Alex has worked a lot on what's list decoding, and so with list decoding you can a lot improve the constant, and at the end really what matters is the actual error probability, and it doesn't just matter the scaling. It doesn't really change these exponents, but it does change what you can actually achieve, and so you can still construct very good codes. Okay, so this is probably the worst slide of all, in the sense that these are the most down for both, okay? And pretty much all other parameters, codes behave quite well. But unfortunately, these are also quite important parameters, okay? So there's still something to be done. Good. Now, what about robustness? Okay, so now let's assume, remember, we had the polar code channels. And what we have is we have the observations on the bottom, and we have to do the inference on top. And so what we see on the bottom are the observations, and we can describe them just by log likelihood values. And now we need to do, along the tree, we can do this by message passing, the inference of what this bit will be here, given that we are seeing here. But let's assume that I don't give you the exact observation. Let's assume, because we have noise in the system, because I don't know exactly what the channel is, I'll give you something that is the actual log likelihood, but potentially something that's within a window plus minus delta. Okay, how bad is that? Well, it turns out that when you do this, for example, at nodes that look like the black nodes, repetition nodes, all you do is with the log likelihoods, you add them. Okay, so if you add them, and each of them is plus minus delta, the worst that can happen is that these deltas are aligned, okay, and so the error could be twice as large as in the input, right? So it could happen that if you do that, that you have a factor 2 that the error actually increases. And at the check node sides, it's a little bit more complicated, but if you work it out, you see that exactly the same bound holds. So this means that after one level, the error could go up by a factor 2. And if you go all the way up and do the same thing, you will see that the error could be amplified as much as the block length. So the likelihood that you get, okay, if you don't do the computation exactly, the error might go up as much as the block length that you're working with. Okay, so these are very simple bounds. And in some sense, it's also the best you can do. You can show that there's some that really behave like this, but it's a very pessimistic bound because for most channels, it's clear that you cannot have this worst case. Okay, so it's a very pessimistic bound that you have. So what would this do? Let's assume that's really what you have, and that's the best bound that you have. How bad is that? Well, we have now the log likelihood that we should compute, and then we have an error, right? And now we want to see if this makes a difference in our decision, right? So if you want to know if it makes a difference in the decision, it's important that we know what should we compare this error with, right? If the log likelihood itself, the right value is 1,000,000, and then I have an error of 20, it probably doesn't make much difference, right? But if the log likelihood is, let's say, 10, and we have an error of 20, then clearly this might make a difference. Typically, you simply look at the sign later on and decide if that's a 0 or 1. So the question is, how large will that value, if you did the computation exact, be in a typical case? And I don't want to go through the computation, but you can show that this itself is of the order of square root of n. Okay, so this itself will behave like the square root of n. And so this means that if now the mistake itself gets amplified by a factor n, right, then what we want is that the error is small or is on the same scale as the likelihood itself. Okay, so it means square root of n should be roughly n times the delta. And from this we see that the delta should be of the order, should be small compared to the 1 of the square root of the block length. Okay, so this tells us that, if we, as long as we have this, clearly we will not, this will not really contribute to our error. Right? So that gives us some notion of robustness. And indeed, you can do this. You can do this. So you can. This is a particular channel with particular log likelihoods. You do the simulations. So this is you simply do simulation here, error probability, and you do 2 simulations. One where you know the channel exactly, and one where you just estimate. And the estimates are picked in such a way that the deviation is exactly of 1 over square root of n. And you see that indeed the 2 basically behave the same. Okay, and you can do the same thing for spatially coupled codes, and I don't even want to go through the numbers. And you see that indeed, what we said before in this very pessimistic, typically the delta that can you add. So this is the delta of the epsilon of the log likelihood can you add. So this is about 0.3, and the actual log likelihood is of 0.2. Okay, so this means this is roughly 15% of the value that you randomly add, and you can see that even on that level, it almost doesn't make any difference. Okay, so it's actually fairly stable. Good, so that's good news. So things are fairly robust, and that's good news, particularly if you don't know the channel or you have to estimate it, and so you want clearly robustness. Okay, so now this also relates to how we should construct the channel. Okay, so how will we actually construct these codes? Well, for spatially coupled one typically constructs or one typically analyzes ensemble averages. So you look at an ensemble such codes, you decide or you figure out how this behaves in average. You prove something which is called a concentration, saying that almost all codes behave the same, and that's the analysis. Okay, for polar codes, it's actually slightly nicer because you can construct a particular code completely explicitly. And so the question is, how complicated it is to do that. And indeed, so there are 2 components to it. The first one is that, remember, we had these channels, and we need to figure out which ones are the good and the bad channels. And so the way to do this is the following. You start with the original channel, and these are these n channels that you see here. And it turns out that you can compute if it's good or bad in a recursive manner. You just start with the original one. You split it into 2 cases. You split it again into 2 cases. If you're done on the bottom, then you see the quality of all the n channels that you want. Okay, so that's just the recursive nature, and it was first described in this paper by 2 Japanese authors. So, but what are these steps? Essentially, you should think of them as just convolutions. Okay, so it's not exactly true, but think of them that a channel is just a density, and think of that what in the step you have to do, you have to compute a convolution. Okay, not exactly what happens, but it's very close to what happens. So the question is now, of course, if these are real densities, okay, continuous densities, then of course you cannot compute that. You need to quantize it. You need to somehow split it up. And so what is the effort to do that, and how do you have to quantize it, and what's the complexity in order to get something that's very close to the true value, right? And so indeed, Alex and his postdoc Ido, and then Ido with some authors from EPFL have looked at it. And their schemes are more sophisticated, what I'll tell you now. But since I already told you something, I want to reuse it. One way to think about it, doesn't give you the best bounds, but it's fairly close, is the following. Remember that I told you that these densities live on a support which is roughly of order square root of n in the block length. And remember that I said that I had to pick the quantization of order roughly 1 over square root of n. Okay? If you do that, then basically you do the computation exactly. Well, this means that there will be n points that you have to pick. And if you have to compute a convolution, it means your complexity should be of order n log n. If you do it faster, perhaps n squared. Okay, so it means if you did convolutions in that sense, right? So you have a density, and now instead of picking the exact continuous distribution, you simply pick deltas here, and you pick it as fine, and you pick it on that support. Then after the n steps you're doing, then essentially you will get the same result as you had beforehand. Okay, so just from what we said beforehand. So if you believe that, and you believe that we need n log n such convolutions in total, it means that the total complexity in real operations should be n squared log 2 of n. Okay, so it's all a little bit rough here. And so now the question is, if we want to get delta close to capacity, what does this really mean in complexity? Because we're not interested in the block length. We're interested in, we want to get delta close to capacity. So what block length do we need? Well, as we talked about before, and the block length that we need is roughly n is 1 over delta fourth, right? I told you that in the gap to capacity, the block length that it needs is 1 over delta fourth. So if you plug it in, you see that you get something like, it's computable, forget about the log factors. In this case, it's 1 over delta to the 8th, okay? So this is not the best you can do. You can do better, okay? And this is also not the scheme in which Alex and Emmer and his co-authors derived it. But the important thing is that in principle, there's a deterministic scheme of how you can compute which channel is good, which is bad, and you have bounds on all the things you want, okay? Now, clearly you see you want something that's significantly better than that. Even 1 over delta fourth probably wouldn't be fantastic if you want to do it because, if, let's say, think of delta as 0.001 or something like that, the complexity can blow up. But it's doable, and it's deterministic and everything, okay? So that's quite nice. Good. Now, so far, I've told you about the robustness and what's the complexity to compute. But sometimes in practice, you might, so far I've always told you how fine do you have to compute everything if you want to basically get optimum performance, right? So if you do it as finely as I told you, there's no loss essentially up to higher orders. But sometimes we want something even better, right? Think of, for example, optical communication that works maybe at 100 gigabits per second. You cannot afford to have a, 10-bit decoder perhaps, okay, at these speeds. Maybe you just have 1 or 2 bits. And so the question is, how good do things behave then? And so you can look at, this. So for example, if we take a very extreme case with polar codes, and let's assume all I allow you to do is to have basically 3 messages, okay? Either I think it's plus, I think it's minus, and maybe I allow you to have an erasure. That's all, okay? So, we have now gone from infinite computation to something that I only allow you in the decoding, in the steps, in the inference to 3 messages, okay? So that's essentially the worst you can do. If you do less than that, you can show that there's nothing you can achieve. And so the question is, how much do you lose? And so this is what I show you here, this is the capacity here. So this is, you should achieve this, the 45-degree line. And then these are for various channels how much you can actually achieve. So this is how much you actually can achieve. For the BSC, that's optimum. You only need 3 messages. But you can see that even for other channels, even this very radical decoder achieves a decent fraction. So particularly, for example, if you think of the BSC and you're up here at higher rates, there's almost nothing lost by just doing this very, very compressed computation rather than doing optimum infinite precision. Okay, so this is actually quite robust against quantization. And so you can show, and this should be true in both, but nobody has worked it out here, that if you want to get delta close to capacity and you just have a fixed number of bits, all you need is log 1 over delta bits to do the computation. Okay, so that scales actually very nicely and is again very, very robust. Good. Now, throughput. Polar codes are inherently sequential. You do one thing at a time, okay? Versus spatially coupled one is inherently parallel. So I guess unless you again do something, it's much easier if you think, for example, of very high-speed applications like 100 gigabits per second throughput for optical to do it in this scheme than this scheme here. Although I suspect that in both of them, you probably can do the same thing. So we'll see in a second, the price that you pay here will be that the complexity here will be smaller compared to this. And it would be interesting to find decoders which, there's probably a way to decode polar codes with higher complexity, but more parallel. And there's probably also a way to compute spatially coupled codes with lower complexity, but serial. And I would not be surprised if at the end you get the same if you're actually looking at the same throughput. OK, so this brings us to complexity. Polar codes, it's quite nice. Okay, so you need of the order if you want to be delta close to capacity. It scales like log 1 over delta, maybe some power here. And this is just already number of binary operations. That's not even the number of real operations, but that already takes into account that you can do quantized operations, as I talked about beforehand, right? And so that's a very nice scaling, and you probably cannot do much better than that. Now, but that's a serial decoder, where you basically decode 1 bit at a time. As I said, spatially coupled codes, you can have much higher throughput, but you do pay a price. And the price is that now the number of iterations that you need to do scales like 1 over delta, okay, which is much worse than log 1 over delta. And so in general, the decoding complexity here, if I do number of operations, is larger than what I do here. And also that, of course, can play a role if you think of bit, or if you think of chips these days that you build. Sometimes the real bottleneck might be simply energy that you can dissipate, the number, whatever joules per bit decoding that you can have. And so if you have more operations, presumably that might become a bottleneck too. OK, what about universality? OK, so if you look at spatially coupled codes, then what happens here is that let's assume I'm looking at a capacity of a half. And let's assume I look at various channels. Then what happens is if I'm looking at very simple codes, remember, so for capacity half, what I should see here is that that's the optimum rate I should be able to achieve. I can compute what the thresholds are. And you can see that no matter what code I use, that's already fairly close to capacity. And in particular, if I go to higher degrees, you can see that these become even better and becomes even better. And you can see that you get very, very close to capacity. Indeed, you can show that if you take spatially coupled codes, then the rate that you can achieve, and that's universally for all channels, is capacity minus a term. And this term has e to the minus, and this is the degree in there. All the rest is basically a constant. Okay? So you can see that exponentially fast in the degree, this you will be able to universally achieve the capacity of all these channels. Doesn't matter which channel you have. Okay? So you don't need to know when you construct what channel you will construct it for. So that's quite nice. So spatially coupled codes are universal by design. There's nothing you have to do. What about polar codes? Well, polar codes is a little bit more complicated. Why? Remember, I told you we had this picture here. And so I told you that no matter what the channel is, there will be a blob here of good channels. And that fraction will be very close to capacity. So let's assume that's for the BEC of rate half, of capacity half. That's for the BEC of capacity half. In both cases, the set of good channels will be very close to a half. Now, unfortunately, what happens is that these channels are not exactly aligned. They're not the same indices, which are good for polar codes for BEC and for BAC. And so if you look at what's the intersection, so the ones that are good for both, unfortunately, you can compute this. This is not equal to capacity. Okay? So in general, polar codes themselves, if you don't do anything particular, they're not universal. So, OK, so of course, again, there's something that can be done. And I'll just, for example, Lily, who is in the audience with Aaron, who was also here as a postdoc, worked on that. And so there are a few schemes. I don't go into how you can make polar codes universal. So there are ways to make them universal. But it comes at a price. Essentially, the price is that the block length, again, increases. Okay? So roughly, the block length becomes a square larger. And so that's, of course, so it means that all these schemes still have low complexity. They are still, in the polar sense, good codes. But in terms of practicality, if you really wanted universality, the block length, which is already not very good for polar codes, becomes even worse. And so there's still, I think, a nice, interesting open question of how to find the optimum ways. Although, let's say, in a theoretical sense, all these things solve it. But I think in a practical sense, there's still something to be done. OK, now let's come to the most important measure, popularity. OK, so both of them have been on arXiv. You can look at it. OK, and so there are, for both of them, you have quite some papers. And I think if you're interested and you go to arXiv, you probably find most of the relevant papers on there. And so that's quite a nice resource.
How many of these are from your group?
1, 2, I don't know. OK, now maybe one measure still, right? So if one thing I did, I simply looked at all the titles and then put them for Wordle. So that is basically a set. You can look. I took out the most obvious one, of course, polar and so on, because that would dominate the whole picture. For both of them, there's an amazing list of applications. Okay, so there's almost, and you can ask Lely, who is, for example, an expert here, or Alex, who is an expert here on all the applications from security, for example, where Alex worked, the wiretap channel, to many of the network information fear problems that, for example, Lely worked on. There's almost, and that's quite nice in particular for polar codes, there's almost no scenario, or I actually don't know any scenario for which we know the capacity and for which not, and certainly typically for polar codes, it's very easy to prove typically that you can, well, easy, okay, it's possible to prove, and typically not too many pages, that you can actually achieve in low complexity whatever we know from information theory. Okay, so that's, I think, a very, very nice thing about this code. Typically for spatially coupled, it takes more effort to do it. But there's really, I don't know of anything, if it's asymmetric channels, networks, you know, I mean, no matter what you can think of, source coding, all of these problems, if we know the capacity, these two schemes typically will achieve it, and they will achieve it with low complexity. So that's quite nice to have. Good. Now, let me summarize a little bit. If I look at the two, I would say that, you know, really most of it looks actually quite nice, okay? But I think there's really one thing that, you know, we still have to look at, and so that also brings me to basically the biggest open challenge. I think if you really want to bring them into, you know, a product, I would say in both cases, the biggest open challenge is to come up still with constructions that, for either polar or spatially coupled one, that will then make them very good for short lengths. You know, as I mentioned before, and Alex, for example, worked on the list decoding, and there's a lot of things you can do. But I think there's still some open challenge there to really make them as good or better or significantly better than currently optimized LDBC codes that are already used in practice and already you can find in products. And so that's, for me, probably the biggest still open and worthy problem. If you think about the more information theoretic side, if you think about just the side of how proving just that with low complexity, very low complexity, you can achieve capacity of pretty much all the channels we know, you know, a lot of it is already known, and I think there's still some nice open problems, but I'm very confident that there we can do all this. I think this, to me, is still probably will need some additional ideas, can still need quite some extra work, but I think from a practical side, that's something I think that's very, very important, and it will make a difference whether or not, you know, we stay simply on the archive side or whether we go to the, you know, side of whatever, Qualcomm or Samsung or whatever the companies that might use it and put this in the product. Okay, and so that brings me to the end, and I'm done. Thank you very much. Okay.
You probably said this, but could you make a short statement to explain what the advantage of coupling is? In other words, is it simpler decoding, shorter code lengths, whatever?
Yeah.
Because
right. Right, absolutely. So, okay, so the first one is so what happens? If you decode, if you pick your favorite code and you do this coupling, then this code, if you now use the standard iterative decoder, it will behave as well, the threshold will be as large as if you had decoded the underlying code under map decoding. So the threshold typically is significantly better. Now, so what does this end plus the code will be universal? So what would you have to do for, let's assume universality was an important issue, okay? So you want the code that's, think for example as a multi-access channel, perhaps you don't know what the channel gains are on the two things, you just know that they're such that information theoretically should be able to decode. If you wanted to have, let's say, a code for this scenario, depending on what the channel codes were, you would have to design the degree distribution in such a way that the iterative decoder would converge. Versus here, it doesn't matter. You just have one code. As long as the channel gains are in the regime in which information theory tells you that you should be able to decode, you will be able to decode. So universality is one thing. Perhaps that's important in some scenarios, perhaps not. The other one is that typically for standard LDBC codes, you have a tension between the error floor and a good threshold. So typically, you have to pick a very clear degree distribution, and there's a tension that if you want very good thresholds for large codes, then typically the error, you know, you have to control the error floor. So think of a scenario in which you have to have a very good control of the error floor. Maybe it's storage and it should be 10 to the minus 15, but you still want to have good threshold. Now, for spatially coupled, the relationship goes exactly in the opposite direction. For spatially coupled, if you increase the degrees of the underlying graph, then the threshold becomes better because the code itself becomes better and the map behavior of the code becomes better. And so versus for if you did it uncoupled, if you increase the degrees, typically the iterative threshold becomes worse. So the error floor becomes worse. In both cases, the threshold, the waterfall behavior becomes worse. So in both cases, the error floor becomes better. But for LDBC codes, there's a tension between error floor and the threshold. Versus if you do map decoding, the two are aligned, they go in the same direction. So having increased degrees will improve both of them. So in principle, it should be easy to construct codes that have very good error floor and very good thresholds, okay? And so that might be another thing, but as I said, one price that you have to pay, and so that's also another nice research question. You basically want to minimize the rate loss that you have by getting this process started, okay? So, because that's something that bounds you away from capacity, and so if that's very large, then the code itself might be the perfect code, but if you lose a lot there, you're already dead before you start. And so you have to come up with good schemes to how to get the ball rolling. And so what is the minimum energy? What's the minimum number of information that you have to put in there? And so if you can minimize that, then you can minimize the rate loss. If there was no rate loss, then these codes would be essentially capacity achieving. I mean, they would be basically as good as the optimum codes. You would have the 1 over delta squared scaling and everything. But it's really the rate loss that bounds you away. So there's also still an interesting question.
Talking about finite length scaling, do you actually know how to design a code with, say, 1 over delta squared, random code, if you ignore the complexity?
Right.
So is it possible that perhaps there is a fundamental trade-off between decoding complexity and finite length scaling?
Right. It's possible, but I think it depends also exactly on what scaling you look at, because of course, if you look at, I think the right scaling is exactly that scaling that I talked about, where you look at the delta, the gap to capacity versus block length versus error probability, right? If you look at different scalings, then of course you can always play the game where you, for example, have an inner code that gets you very good to close already, and then you have an outer code to clean things off. Okay, so that's a slightly different scaling, and so you need to really think of that. How does it behave as 1 over delta? And yeah, perhaps there's a fundamental trade-off there, and perhaps there's just no way to do better than something, right? We have now seen you can maybe get 1 over delta third, but I don't see any reason right now where that would be the optimum thing, right? So unless we have a real bound that says that that's the best one, I think it would be interesting to see, right? And also, I think one needs to be careful not to. I think it's very nice to see the scaling, but we know that, of course, at the end, all you want is really numbers, right? You're not interested. I mean, you're not interested in all codes of all lengths, and so there's a lot of things you can do with the constants, and one shouldn't ignore that. Okay, so because if you can get the constants to be very good, perhaps it's 1 over delta third, but at the end, you're transmitting at maybe length 1,000, maybe 10 to the minus 5, and and that's it. Okay.
We're really happy to have Ruediger here, and we want to thank you for the wonderful talk. And here are some gifts we brought you.
Thank you very much. That's very kind. Can I open it or?
Sure, please.
Okay. Let's see. Did you pick it or did Alon pick it?
It's a secret.
Oh, I see. I'm just trying to see what to expect. Okay. Let's see. What could it possibly be? Ah, it's another blue shirt. I see. Okay. Thank you very much. Okay. Thanks a lot.
So thank you very much again, Ruediger, for the excellent talk. And just in case you don't know, Ruediger is also going to speak tomorrow morning at the CWC review. And I know from his preparation that it's going to be like a hands-on presentation. So I think it's going to be interesting. And there's only one part left, and I think it's a Shannon. Sorry? Oh, there is. Okay. In fact, it's right here, Ruediger. Okay. All right. So I'm sorry. This is not a shirt, so I apologize.
Is it blue too? No. Thank you very much. Okay. Thanks a lot. Very beautiful with my picture, of course.
Okay. And for the last part, let me call Young Han to continue.
So once again, I'd like to thank Rudy for giving us a fantastic talk. I mean, we can really listen to him for hours and hours, and luckily we have, 30 more minutes tomorrow from 10:30, and he'll he ditched kryptonite today because Superman was not strong enough, or maybe Superman was strong enough, and tomorrow he's gonna ditch diamonds. Okay, so I mean, let me just introduce the last event of the day. So Jack Wolf started the wonderful tradition of all this lectureship program, and part of it, he actually started awarding one of our Finite students to something called Shannon Memorial Fellowship. So this year, Paul Siegel, myself, and Massimo Franceschetti were the committee to selecting our students in the general area of communication theory and systems. And somehow this year's job was rather easy, not because the competition was not fierce, but because our candidate was extremely strong and deserving. And this year's award winner is Anand Tirthasrashi, working with Professor Alon Litsky. So that's all congratulating. And before we give him the actual award and actually the check coming with the award, I'd like to bring up Professor Alon Litsky once again so he can say a few nice words about it.
Oh, I don't know, looks like my fate today is to introduce people, so, but luckily for you, this one is, had obviously less time to prepare, so maybe it's going to be shorter than the previous introduction, but not much shorter. So as Young Han was just mentioned, we have a lot of really excellent students here, and many of them are also deserving of the award, and so they may wonder how come Ananda, as we call him, Tirtha, got it. So when I think about it, I think it's actually, there's a very simple explanation, so I just want to tell you just in case you're trying to get it next year. So there are actually just 3 parts to how he got the award. The first part is how he got interested in information theory. Second part is how he got to UCSD, and the third part is how he wrote his first ISIT paper. So I'll just tell you what they are, and I think you can figure out the rest yourselves. So how did he get interested in information theory? So when he was an undergrad at IIT Madras, he did an internship at IISc in Bangalore, and he ended up working on cryptography. So he was there for 3 months, and in those 3 months, he actually wrote 4 papers. And so at the end of those 3 months, he said that he was not interested in being in a field where you can write a paper every 3 weeks. So he said, okay, I'm going to work on information theory. So that's how he got to information theory. And how did he get to UCSD? Well, so he studied engineering physics at Madras, and he was #1 in his class. I think his GPA there, his major GPA was like 10 minus epsilon, something like that. And so when he applied to grad school, he got into some of the very best schools. And some schools are a little more conscientious about the students than we are. And the professor called him, but I guess Tirtha was answering on his cell phone, and the connection was pretty bad. So they didn't get to communicate. So then they called him again. And again, the connection was good. Obviously, they were not using Qualcomm technology, I guess. So that's how we got to UCSD. And how did he get to write his first ISIT paper? So we have some other excellent students in our group, of course, as you know. And so the deadline, of course, everything is done, at least in our group, always we're lucky if we do it before the deadline. So this is now, we're talking one week before the deadline to one of the ISITs. And the ISITs are usually held in pretty nice places like Hawaii and Istanbul and St. Petersburg. So the other 3 students were working on their papers 1 week before the deadline, and Tirtha was not thinking of something for ISIT. So they said, oh, don't worry, Tirtha, we'll Skype you from the beach or something like that. And then the other person said, oh, Tirtha, what's your shirt size? We'll send you a shirt. So Tirtha said, okay, let me think. So he spent 1 day, so this is a week before, he spends 1 day doing, looking at the literature, and then another day thinking, oh, what's interesting, and then, so up 2 days, and then another 3 days. So the second day he figured out what he wants to do. 3 more days he's sitting down writing, thinking, improving the results. The last 2 days he's sitting down typing, and then 5 minutes before the deadline he uploads the paper. Of course the paper is as good the shape, if not better than the other papers, and the paper gets accepted. And if you want to see what the paper is about, you can go and see Tirsta's poster tomorrow. And of course, that's also when we figured out why he didn't like cryptography, a field where you get a paper every 3 weeks. So we figured out why he was not interested in that field. So I think as you can see from these things, I think we have a really exceptional student in Tirta. I mean, he has both has the curiosity to go and find things, the ability to see what's interesting, the technical know-how and talent to prove things and then to explain things and write them really well. So I think he's really deserving of this award, and I think we look forward to great things coming out of Tirta. So Tirta, if you want, you can come. Thanks. Yeah.
So I guess I should thank Alon for a very kind introduction. What he can say is, like, even if he goes to the last moment, he'll be sitting with you and writing a paper. So without his excellent advice, it could not have been possible. And one of the main reasons I came to CSK was to work with him. So, and I should also thank committee members, Yang Han Kim, Paul Siegel, and Massimo Franceschi for the fellowship. And all my lab mates and previous lab mates, Jagav, Hirakendu, Alan, and Ashkan. So thanks, everyone.
Okay, so Tirta, I was just told that the check is in the mail, so you'll get it very soon. So I think we're probably done and for today, and hope to see many of you tomorrow morning, and we'll hear more about Rudy's work and some others. So thank you very much, everyone. Thank you.